Imagine a stadium-sized asteroid spotted 2 weeks out. Suddenly, a fireball brighter than the sun enters the atmosphere at 60 times the speed of sound. Even at this moderate size, the impact hits with the kinetic force of 4,000 historical nuclear blasts, instantly flattening cities and killing millions. These objects routinely slip past our detection grids. In 2019, a 30-story asteroid named OK was discovered just 1 day before it grazed Earth. Last year, an even larger one was spotted a mere 13 days out. If either of those trajectories had shifted slightly, they would have hit us. Despite these warnings, humanity currently has 0 active, deployable plans to survive a sudden impact. Scientists have mapped out plenty of theories to steer these rocks away. They've proposed painting the surface, attaching rocket thrusters, or scorching it with lasers. Colliding standard spacecraft into a fast-moving object is like deflecting a cargo ship by throwing a bag of potatoes at it. You move the target by a tiny fraction of a degree. To make it miss Earth, you must act decades in advance. With only 14 days to react, gently nudging the rock over a massive distance is mathematically impossible. We need a faster option. Most asteroids aren't actually solid stones. They are loosely packed collections of gravel, dust, and pebbles, barely held together by their own gravity. That structural weakness suggests we could pulverize them with a nuclear weapon. But asteroids travel at up to 70,000 kilometers per hour. If we attempt a head-on collision, that extreme speed crushes our weapon into scrap metal before the timer even triggers the detonation. Detonating the bomb just above the surface doesn't work either. In the vacuum of space, there is no air to carry a concussive shockwave. The blast makes a crater, but the vast majority of the energy simply dissipates into space. The classic Hollywood solution of landing a crew and drilling into the core ignores the harsh realities of spaceflight. We fail about 70% of our landing attempts on a well-mapped planet like Mars. Trying to landing on and drilling into a tumbling microgravity rock within 2 weeks is a guaranteed mission failure. Brute force explosions and sci-fi heroics clash directly with the cold mechanics of space. To survive, we have to stop fighting the rock's immense speed and start using it. Instead of trying to nudge the object or blow up its surface, we need to act like a lumberjack. You don't split a log by hitting it with a blunt rock. You use a dense wedge to break it apart from the inside. Our cosmic wedges are called penetrators, slim 2-meter-long cylinders made of tungsten, a metal significantly denser and harder than space rock. We don't even need to shoot them. We just park the penetrator in the asteroid's path. From the asteroid's perspective, it's sitting still, and our dense tungsten bullet is rushing directly at it at 70,000 kilometers per hour. We have to initiate this collision roughly 2 million kilometers away, 4 times further than the moon. If we do it too close, the fragments will hit our atmosphere all at once, combining their shockwaves to kill millions. Upon impact, the violent crash releases the kinetic energy of over 120 tons of TNT. The tungsten melts, carving a deep tunnel through the rock, blasting the loosely packed asteroid into thousands of diffuse pieces. A day later, those fragments safely burn up as a global meteor shower. By weaponizing the asteroid's own momentum, current technology can cleanly neutralize a stadium-sized threat. A different class of threat exists in the outer solar system, mountain-sized comets traveling at twice the speed of an asteroid. These are objects so massive and powerful that a single strike ends most life on Earth. Because they are so dark and distant, tracking them is incredibly difficult. In 2020, the comet Neowise was discovered a mere 4 months before its closest approach to Earth. This diagram visualizes the scale of the math problem. Vaporizing a mountain requires hundreds of thousands of penetrators, demanding at least 24,000 super heavy rockets to lift them. Today, we have exactly 2. Even if every factory on Earth switched entirely to building rockets, we wouldn't finish in time. Against the overwhelming mass of a planet killer, pure kinetic methods leave us completely defenseless. Since a single impactor is too small for a mountain, and space lacks air to carry a nuke's shockwave, we have to deliver the explosion inside the comet's mass. This requires a hybrid mission, a heavy rocket, like NASA's SLS, carrying both penetrators and a nuclear payload. A small team of astronauts launches to intercept the comet beyond the orbit of Mars. Because of the vast distance and the required 5-month transit time, this is a strict one-way trip with no journey home. This diagram outlines the precise engineering challenge. The astronauts must deploy 5 massive penetrators, aligning them perfectly in sequence, exactly 2 kilometers apart, directly into the comet's incoming path. Hitting a target moving at 140,000 kilometers per hour with 5 sequential objects requires absolute precision. In this mission, there is 0 margin of error. The ice mountain smashes into the first penetrator, unleashing the kinetic force of 2,000 tons of TNT. Rock, ice, and tungsten liquefy instantly, gouging a crater dozens of meters deep. A fraction of a second later, the second penetrator strikes the exact same spot, punching further into the crater. The third and fourth follow, melting and smashing a tunnel 100 meters into the monster's core. Finally, the 5th penetrator enters. This one carries a 300 megaton nuclear warhead, 20,000 times more powerful than the bomb dropped on Hiroshima. It flies unimpeded down the freshly carved tunnel. Just before it hits the end, it detonates. Because the explosion happens deep inside the mountain, the vacuum of space is no longer a problem. The immense weight of the surrounding rock and ice contains the shockwave, forcing the energy to crush outward, vaporizing the comet from within. The rockets, engineering, and physics to dismantle a mountain in space already exist. We don't need science fiction to survive. We just need the foresight to prepare.